Task 7, we have a first order system of ordinary differential equations, and this models an engineering problem. What we want to do is to write down the general solution for this system of ordinary differential equations. And in general, if we have a system of this form, where u1 and u2 prime are the derivatives of the functions u1 and u2, and at the right hand side we have this coefficient matrix times the u1, u2. The general solution is c1, which is a number, a constant, times the exponential to the power of lambda 1 times t, where lambda 1 is an eigenvalue of the coefficient matrix, plus, so it's c1 times e to the power of lambda 1 times t. Lambda 1 is an eigenvalue of the coefficient matrix. v1 is the corresponding eigenvector to the eigenvalue lambda 1, plus the second term here is c2 times the exponential, and here the power is lambda 2 times t, where lambda 2 is the second eigenvalue of this matrix, times v2, which is the eigenvector associated to the eigenvalue lambda 2. So first, step number 1, we take a minus lambda I, and this matrix is 1 minus lambda, 2, 2, and 1 minus lambda. The determinant of this matrix is the following. We have to calculate this determinant, and we will get the characteristic polynomial of lambda. So it's going to be 1 minus lambda squared minus 2 times 2. That's lambda minus 1 squared. I can turn this around, minus 4. So that's lambda minus 1 squared minus 2 squared. And that's the difference of 2 squares. So it's going to be lambda minus 1 minus 2 times lambda minus 1 plus 2 is equal to 0. And I have to take lambda minus 1 minus 2 equals 0. So from here lambda 1 is equal to 3, or lambda minus 1 plus 2 equals 0, lambda plus 1 equals 0, lambda 2 is equal to minus 1. So the spectrum of the matrix A minus lambda I, so the spectrum of the matrix A, the eigenvalues is lambda 1, lambda 2, 3, and minus 1. Now we go ahead and we need to find the eigenvector that corresponds to eigenvalue lambda 1. So we take this matrix here, and instead of lambda we put the lambda 1. So we have 1 minus lambda 1, 2, so lambda 1 is 3 here, 1 minus lambda 1, psi 1, psi 2 equals 0 and 0. So it's going to be minus 2, 2, 2, and minus 2, because lambda 1 is 3. So this entry is going to be minus 2, and this entry is going to be minus 2 as well, times this is my eigenvector psi 1, psi 2 equals 0, 0. From here I can write minus 2 psi 1 plus 2 psi 2 equals 0, and 2 psi 1 minus 2 psi 2 is equal to 0, and from here I can obtain that psi 1 is equal to psi 2. So my eigenvector v1 is psi 1, psi 2. This can be written as psi 1, psi 1, and I can pull psi 1 outside, and I have 1, 1. So for psi 1 equals 1, my eigenvector is going to be 1, 1. And now I have to find the eigenvector which corresponds to the eigenvalue lambda 2 equals minus 1. It's going to be 1 minus lambda 2. The first row is 1 minus lambda 2, 2, and the second row is 2, 1 minus lambda 2, xi 1, xi 2 equals 0, 0. So what we care about is the diagonal of this matrix. 1 minus minus 1 is going to be 2. The first row is 2. And the second row consists of 2 and 2 times xi 1, xi 2 equals 0, 0. From here I get only one relationship. 2 xi 1 plus 2 xi 2 is equal to 0. From here I get xi 1 plus xi 2 is equal to 0, and xi 2 equals minus xi 1. My eigenvector v2 consequently is going to be xi 1, xi 2, xi 1 minus xi 1. I can pull xi 1 outside and I have 1 minus 1. And if I put xi 1 equals 1, my v2 is gonna be 1 minus 1. It's pretty much everything I need to know. All the information is here. So I have that u1t u2 of t equals c1 e to the power of lambda 1 times t. Then I have times the eigenvector v1 plus c2 e to the power of lambda 2 times t times the eigenvector v2. The eigenvalue lambda 1 is 3, so it's going to be to the power of 3t times the eigenvector is 1, 1 plus c2 times e to the power of minus t times 1 minus 1 let's write it more clearly underneath. So this is my general solution. Where C1 and C2 are just real numbers. And I have finished at this point with my exercise.